Moving on with graphing logarithmic functions, we're going to work some more examples by graphing them using the transformations that we've learned in the past. And so I have a second example here, log base 5 of 2 times x plus 4. Okay, so I want you to pause the video and I want to see if you can come up with all of this on your own. Okay, the first thing to note is what is the parent function? Well, the parent function is log base 5 of x. And so that's going to be important because I need to know how to shift it. So if I wanted to graph log base 5 of x, notice I would have the point 1, 0. If I were to plug in 5, I would get the value 1. If I were to plug in 1/5, I would get the value -1. And I could continue going on. But I believe this is enough to give me the parent function of log base 5. Okay, what do I need to do with this? When I go to actually transform this, I need to convert the inside as one expression. So I'm going to do that as 2 times my x plus 2. Remember, your stretching and your shrinking on the inside is going to affect your shift. And so this is actually going to be best written as log base 5 of 2 times x plus 2. So originally you thought your graph would shift left 4. Once you put it in this correct format, you realize it's actually going to shift left 2 units. Okay, so we just said that the 2 on the inside is going to make it shrink horizontally by 2, which will be not quite as visual as you hope it to be. It's going to smush it this way, but if you can imagine smushing this image that way, it actually doesn't look like it smushes any. It's just going to change the shape of it a bit. And then we already said once we put it in this form, the other 2 on the inside is going to make it shift left 2 units. So basically, we're going to take all of our coordinates and we're going to divide them by 2, and then we're going to subtract 2. So if I take this point here, and if I take my x coordinate and divide it by 2, that gives me 1/2. And then if I shift it left 2, that gives me -1 and 1/2. If I take my 5 coordinate, if I divide it by 2, that gives me 2.5. And then if I shift it left 2 units, that gives me 1/2. If I were to plot the point 25, 2, which I chose not to because it wouldn't have fit on the graph, if I divide it in half, that would give me 12.5. And if I shift it left 2 units, that would give me 10.5. So it's just barely off the chart here. So 10.5 and 2. So that's going to be another coordinate that I can include now. If I take this coordinate here, if I divide it in half, it only gets closer to my y-axis, so that's hard to see. But then if I shift it left 2 units, that's going to put me right here. And so I believe this gives me enough to give me the shape of my graph. Let me try and connect all these points in red. And so this is the shape of my log function. If you want to double check this by using your calculator, I encourage you to do so. You just need to remember to use your change of base formula because this is base 5, so you need to convert it into base 10. So on my graph here, I have my original, my parent function, which is log x over log 5. That's my change of base formula. Let's see what happens when I put in my transformed function. Again, I used my change of base formula, but let's see if it did what we thought it should do. And there we go. So it did smush it horizontally, even though that's very hard to see, but we also now can see that it shifts 2 units to the left rather than the 4 maybe that you originally thought. All right, so our graph resembles what's happening with these graphs. So let's see if we can come up with our domain, which is now, since I shifted it left 2 units, my vertical asymptote is now at x equals -2. So maybe that's the thing I'll fill in first. Which means my domain is -2 to infinity. And my range is still defined for all y values. My intercept, if we see it here, might be hard to figure out what exactly that intercept is, but we already did the math. We took the x-coordinate of 1, we divided it by 2, and then we subtracted 2. So we have 1/2 minus 2, which was -3/2. And so my intercept is at -3/2, 0. I'm going to do one more example of these. And this one is using the natural log function. So we have 3 minus 1/2 the natural log of x. Remember, the natural log is opposite of e to the x. And so if you wanted to figure out what the basic shape of natural log of x is, that's very easy to do. We just flip the function of e to the x over the line y equals x. And so that gave you the answer to the first question. What's the parent function? And if we wanted to graph natural log of x, we know that we're going to have the point at 1, 0. We know that this is the opposite of e, which is 2.7. So my first point is going to be 2.7 and 1. If I were to actually take that and square it, that would actually give me around 7.5. So that's going to be my second point, 7.5 and 2. So this is my parent function, the natural log of x. I'm just inverting e to the x. And so now I want to transform it. So I suggest that you pause the video and work that on your own. Okay, so if I rewrite this as -1/2 natural log of x plus 3, it might be a little bit more obvious what we're doing. The plus 3 is going to make your graph shift up 3. But before we do that, we need to worry about this here. Multiplication always before addition and subtraction. Since those are on the outside, they're going to affect it vertically. The negative is going to make it reflect over the x-axis. And the 1/2 is going to shrink it vertically by 2 units. Okay, so let's see if we can do this math here. Let's start with my first y-intercept. I'm going to reflect it over the x-axis, puts me in the same place. Shrink it vertically, still puts me in the same place, and then shift it up 3 units. So 1, 2, 3. Okay. If I take my next coordinate, if I reflect it over my x-axis, that puts me here. If I shrink it vertically, that puts me here. And then if I shift it up 3, 1, 2, 3, that puts me there. If I take my next point, reflect it, puts me here. Shrink it, puts me here. Shifting up 3, 1, 2, puts me at the exact same point, which is really interesting. If I take another coordinate over here, and reflect it, goes up here, shrink it, goes up here, and then shift it up 3. 1, 2, 3. Puts me right there. And so I believe this gives me enough to show me what this log function looks like. So the new one is my green graph, the old one is my blue graph. Okay, let's start with the asymptote, since that's always seemed to be the most important. Notice our asymptote didn't change, so we still have our vertical asymptote at x equals 0, which tells us that our domain is still 0 to infinity. Our y values are still forever, so -infinity to infinity. And the only thing that we have to worry about here is the x-intercept. And it's going to be so far out there that I'm not even going to really worry about it at this time. And so I believe that we have worked through everything that we need to work through in defining logs. We explained its definition, we worked some values, we learned about the common log, which is base 10, the natural log, which is base E. We've learned some basic properties, and we've learned how to graph them using transformations. And so I think this summarizes this set of videos.